third part of chapter 2 about the Catalan garden. So this will be the main ingredient all along this chapter, the cyclic lemma. It can be stated in terms of Dick words or in terms of Lukasiewicz words. So first I will introduce some elementary definition. We are in the free monoid generated by the alphabet X, and we say that two words W prime are conjugate if and only if you can write W equal UV and W prime equal VU. So conjugation of words means you take a word, you cut it, and you exchange the two left and the right part. And this is an equivalence relation. It's easy to check that the conjugate of a conjugate is going to be itself a conjugate. Now to say a word is primitive means that if you can write the word as a power of another word U, then P equal 1. So primitive means you cannot write the word W as a power of another word. An elementary lemma to say that a word is primitive is equivalent to say that all its conjugates are distinct. Little lemma. I leave you to check this. So to say that all the conjugates are distinct, so if the word is of length n, there is n different conjugate. Each time you cut, you will get a different word. And this is equivalent to say that the word is primitive. You see, if you take a power of the word U for P bigger or equal to 2, then you will have many conjugates the same. You cut at any between two U, and then so cutting a word and exchanging the two parts means maybe you will have different cutting, but giving the same word, the same conjugate. Here, P times you will obtain the same word. So I will introduce an extra notation to distinguish between when I cut and two different cuts give me the same word. I will introduce a label conjugate, means that it's a conjugate, but you remember where you cut. So label conjugates, if you have a word W of length n, all the letters x1, x2, xn are with alphabet X. I cut after the letter xi, I reverse the two U and V, and I will call label, means I remember where I cut. So two different label conjugates can give the same conjugate in the case the word is not primitive. So I will go back to D, the set of Dick words, all Dick words which are counted by Catalan numbers, Dick words of length n. And I will introduce the language A. A is a Dick word, any Dick word followed by an X bar. So it's a kind of a Lukasiewicz word, if you remember the definition of Lukasiewicz. So you have a Dick word, a Dick path, you see. It's always above the x-axis, and then I finish at the end with an X bar. So I will denote this set of words capital A. And here is a proposition. It's a certain form of the cyclic lemma. The general cyclic lemma in the case of Dick words. So let's take any words in the letter X bar, such that delta of W equal P equal minus P, where delta, what is delta? The map delta is a morphism from the free monoid to the monoid additive monoid of integer, such that delta of X is 1, delta of X bar is minus 1, and the morphism, so delta of a word is going to be the number of occurrence of the letter X in W minus number of occurrence of the letter X bar. And to say that delta of W equal minus P means that if I look at the path related to the word. At the end, the path is at a level minus p. See, it's like this. Here is a general word in W, in x bar, and at the end, the level of the last point is minus p, which means that the delta of the W is minus p. So in the cyclic lemma, I suppose delta of W equals minus p, then the lemma says that there are exactly p label conjugate of W such that W belongs to the monoid generated by A. This means that W, the conjugate, no, it should be Wi, sorry, Wi is a product of words in A. In fact, it's going to be a product of P words in A, because each word in A give you a delta equal minus 1. A product of P words will give you delta of the Wi equal minus P. So this is the main lemma to begin this lecture, the cyclic lemma. You take all possible words in x bar so that the exceedance of x to x bar is P. The words, the paths go to level minus P, and then if I take all possible conjugate, they are exactly P different label conjugate. Because maybe if you have x bar, P times, then there is many different label conjugate will give you the same conjugate. So this is why I say there is a P label conjugate, P different label conjugate, such that Wi is a product of words in A. So to understand the lemma, it's better to see with a picture of the path corresponding to the words. So before showing so this lemma was due in 47, Droveskin-Motzkin, and it was used, popularized by Rane, where he proved the Lagrange inversion formula using the cyclic lemma. So we are going to do this today to prove the Lagrange formula with the cyclic lemma. So example, a word of length 4, x bar, x bar. So there is, you go to level minus 2, p equal 2, and there is 4 different conjugate, even some conjugate. 2 of them are a product of words in A. This is in A, this is in A. In A means a dict path followed by a minus 1, by a x bar. So you have this conjugate is not in a product of A, this conjugate is not, but these two are product of A. So there is 2 conjugates which are a product of words in capital A. So how to prove the lemma? It's just to see this picture. So in green, you have the paths which correspond to the word. Each time you go up northeast means you have an x. Each time you go down, you have an x bar. So the path goes like this, and at the end, the level of the last point is minus p. P is a positive integer. So I denote by minus m the minimum level reached by the path. And then there is a certain number, say when you go down from the origin to the minimum level, you have a unique factorization. First, you have a dict path, and then the first time you reach the level minus 1. Then you continue, you can go up and down, and then the first time you reach the level m minus p, etc. So for each red edges is the first time you reach level minus 1, minus 2, minus 3, minus 4, but I am only interested in this p times in this one, d1, d2, d3, etc. until d index p. Is it clear?
D2 is not after D1, there's something in between.
This is D1. The big one?
Oh, the big one.
The big one, when D1 is when I reach the level m minus p.
Okay.
M minus p is the distance between this and this.
Okay, so after that there are p steps more.
After that, here is exactly m minus p. So there is one step going down to m minus p minus 1, and then etc. until minus m. So here there is p step going down. Here the p equals 3. So you have 3 steps to get down to the minimum. I claim that this factorization is going to give me the 3 different conjugates of the word W. So the first conjugate, you put D1, you just take the conjugate, you see. So D1, I was reaching the level m minus p. It was exactly done so that if I put this part of the green, if I put it here, then it will reach the level minus m. But there is one more step, so it will reach the level minus m minus 1. And I claim here I get the product of P, D1, D2, DP, etc. And this big one, I get a product of elements in A. Dic multiplied by x bar, dic multiplied by x bar, and this is a big dic multiplied by x bar. This is the first conjugate. Then the second one, you put D2 at the end. And the PM conjugate, you put DP at the end. So I claim that these are the only possibility to get a product of words in A. And there is P possibility to get conjugate like this. I go back to the general, I repeat the construction. You have the path. The only way to cut the path and get a conjugate is to cut here, here, or here. There's 3 different cuts. P equals 3 here. So the big one here is you reach the level m minus p, which is exactly the distance between these 2 lines, and you add a new edges. So what we are going to get is this big word in dic multiplied by x bar, which gives you a word in A. Each word here is in A, and I have P different conjugate of my word W. And I claim that these are the only way to cut the path, so that if I make the conjugate, I get a product of element in D, no, in A, a dic multiplied by x bar. So this is a cyclic lemma. In the case of dic path, only x and x bar letters, then in the general case where p equal na positive numbers.
In the example which you showed, there were only 2 conjugates.
Yes. The first one? Yes. P equal 2. There was 2 conjugate. And so the unique, this part here, the unique factorization was I cut here. And I cut here. This was D1, D2. D1, D2. So you conjugate.
M is equal to minus p.
M is minus 2. Yes, M equal P in that case. Here P equals 3, M equal minus something. P equals 3, and here there is 3 conjugate.
M minus p is 0.
Here? In the first example, M minus P was 0, yes. So when M minus P is 0, then this part is empty. The first example, this was an empty word. Here. There was only x bar. D1 was reduced to x bar, and D2 was reduced to x bar.
So what you call the big one was empty.
The big one was empty. Okay, so I go to some immediate corollary of the cyclic lemma for dict words with a general P. In the case P equal 1, so what is the total number of paths in x bar such that the delta is -1? You have to choose n times x and n plus 1 times x bar. So the total number of paths is 2n plus 1 choose n. It's any binomial coefficient, any subset of n elements among 2n plus 1. You choose the position of the x. What remains, the other position, you put the x bar. You get a word having one more x bar than x, so you have a word in this of length 2n plus 1. I apply the cyclic lemma. Here P equal 1, so there is only one conjugate, which is in A. And one conjugate in A means it's a dict path. It's a dict path followed by an x bar. So which means the Catalan number is exactly the cardinality of x power 2n plus 1 intersection with the words in A. And among the 2n plus 1 different conjugate, there is only one. So corollary, the Catalan number. There is 2n plus 1 different conjugate, and only one of them will give a word in A. So this gives you a bijective proof of the formula for the Catalan number. This is different. You have a binomial. You don't have 2n chosen. You have 2n plus 1 chosen. It's not exactly the same formula divided by 2n plus 1. So the cyclic lemma tell you that there is 2n plus 1 different conjugate, and only one of them will give you a word in A, which is a dict word of length 2n followed by an x bar. So immediate consequence of the cyclic lemma is give you a bijective proof of this formula for Catalan number.
Can you repeat it once more?
So the total number of words with nx and n plus 1 x bar is equal to this binomial coefficient, which will give you words having delta equal -1. It's go to the level -1 at the end. The cyclic lemma tell you that P equal 1, so there is only one conjugate among all these words which belong to A. And what is A? It's a dict word of length 2n multiplied by x bar. So the cardinality of A, of the word of length 2n plus 1, is exactly the Catalan number. It's dict word of length 2n followed by an x bar. So all these words, only one of them will give you a word in A. So the Catalan number is 1 divided by 2n plus 1 multiplied by the binomial coefficient. Because there is only one conjugate. P equal 1. In general, if you go to level minus P, there will be P different conjugate. But here there is only one. So among all these words, each time there is a class of words. One of them will be in bijection of the dict path, counted by Catalan number. So this is an immediate corollary. Give you bijective proof for the Catalan number.
So what happens if you put delta inverse -2 now?
Okay. Let's do -2. Why not to put minus P?
Yeah.
Okay, so corollary, if I put delta equal -P, this is the answer to your question for any P equal 2, 3, 4, 5, etc. So if you apply the same lemma, so you have a word of length 2m plus P, means there is mx, followed with mx bar, but the number of x bar will be m plus P. Instead of m plus 1, now we have mx and m plus P x bar. So any word having mx and m plus P x bar will be counted by this binomial coefficient. And among all these cyclic conjugate, so total number of cyclic conjugate will be 2m plus P, but only P of them will be in this set, will be a product of word in A, which is this interpreted by this picture. Here you have m northeast step, m plus p southeast step. Here there is 3 more, p equals 3. And among all these words mixing x bar, I have 3 possible words, p equals 3, as a product of word in A. So when I was counting with p equal 1, I was counting dig pass. Now with any p, I am counting dig pass, which would start at any level. So this is the so-called well-known alpha distribution. In this class, there will be today 3 distributions along the Catalan garden, alpha, beta, gamma. So we are working with the first distribution, alpha distribution. The total number of dig words of length 2n, having I occurrence of x at the beginning, is exactly given by this number, which are sometimes called ballot numbers. So I have to show the connection with the p. Before there was an m and a p, now I have changed the notation with I and n. So the connection is the following. So I was counting in the previous slide, I was counting a product of p words like this in A. So now I am counting dig, this is a general dig words, and the statistic is you are counting how many letter x at the beginning. What is the longest sequence of x at the beginning of the word? So any sequence like this, you can write I northeast step followed by a southeast step in red. So I have to count this, and the connection with the p is this. So we have a word x power I, x bar, followed by all this. Then I associate the word v. I put this x bar at the end of ui. So v has length 2n minus I, and v belongs to a power I. And in the previous notation, p is related to I equal p, and 2n plus p equal 2n minus I, m equal n minus I. So you change the variable here, and you get this formula. So it's just a change of notation from the p possible different cyclic words. And here I have a slight change with I, the longest sequence of x northeast step in a dig pass. So this is a well-known distribution among Catalan garden. Why is it called the ballot number? Because of the ballot problem. You have, this was in, usually it's attributed to Bertrand, with another solution by Désiré André in 1887, but it was also before in 1878. So you have 2 votes with 2 candidates A and B, and A is going to win the vote. And what is the probability that all along you take all along the dépouillement, how do you say that A is always ahead of B and there is no tie. The path is strictly below this diagonal, which means the path is weakly below this line. And it is well known that the probability is going to be A minus B divided by A plus B. It's because the number of such paths is the binomial coefficient A plus B choose A, and again I make a change of notation to the ballot problem between n and p and A and B, and if I change this, I get this number coming from the cyclic lemma, give you exactly this. And if probability is this number divided by total number of paths, which gives you this number. So I repeat, the path is strictly below the diagonal, except at the first step, but it's weakly below this dash line. And sometimes these numbers, this ballot number, you can put them in a triangle, which is sometimes called the Catalan triangle. In fact, there is different triangle giving Catalan number. This is one possible Catalan triangle. And you see, I have written dig path. Any dig path, you see, if you follow this such a diagram, so any path here, there will be 28 paths coming here, because there is 14 coming here, plus 14 coming here, it's 28. So the total number of paths reaching any point of the triangle, any let factor of a dig path, total number of paths, will be the sum of the number of paths coming here plus number of paths coming here. So you can very easily put this number in the diagram. Each number is a sum of the number above, just at the left, and the number below, just at the left. 5 and 4, 9, 9 and 5, 14, etc. So, and the first row, you obtain the Catalan number. Amri seems to be dubitative. So usually it's written like this also. When you see the Catalan number appear like this, and each number, each number is the sum above and left. 9 and 5, 14, 14, 14, 28, 3 and 2, 5, etc.
Also in this case, the row sums are also Catalan numbers.
Yes, the row sum are also Catalan number.
That you don't see it here. Okay, How
So
do you understand that?
Exercise, easy exercise. Show that the sum of all these numbers is a Catalan number.
Yes, sure.
The next one, the sum of all these numbers is a Catalan number.
That's just number of big parts.
Because any path coming here, you add this one.
You add that to complete.
So any path arriving here, there is a longest sequence of x bar and there is an x before. So any path coming here can be the sum of such this number. So it's very easy to see that the
So that's exactly what you counted this time. You said Ix is to start with.
it's exactly the ballot number. It's equivalent to count dig paths by the statistic number of longest sequence of x at the beginning or longest sequence of x bar at the end. It's the alpha statistic, and it's the same as a ballot problem when you have any path which is below the diagonal and which finish in any point, not necessarily going back the diagonal. So you can believe maybe this ballot number was in end of the 19th century, but then I discovered that this Catalan triangle, when I was in Taglefleur, I found a book, and this Catalan, this is the same, 1, 1, 1, 2, 2, 1, 3, 5, 5, 1, 4, 9, 14, and this book is in 1800, much earlier than the ballot problem, and much earlier than all the paper by Catalan, Binet, etc. There was many paper in 1835 following a layer paper. So already in this by Arbogast, he was in Strasbourg at the beginning, so very few years after the death of Euler, and you see this triangle. It's page number 214, and you see, he say in the Mémoire de Laplace, in page 267. I tried to find what is this Laplace was working with this Catalan triangle or Catalan numbers. I cannot find in Laplace, but this was too big, many pages to see, and I don't find it. But at least I found this tableau.
What is the context?
I don't know too much. It's about probability. It would be interesting to read more carefully, because it was with the Mémoire of Laplace, Mémoire de Paris, about probability calculus.
What was the title? Du calcul.
Mémoire de Paris.
No, the title of the book.
Ah, calcul des dérivations. Dérivative, différentiel calculus. De l'Institut national, professeur mathématique, math professor at Strasbourg University.
These numbers come up in different.
It's, I don't know. He says these are given by the recurrence relation, exactly the recurrence I showed you before. He constructs a table and the beginning of the following table, each term is a sum of the, well, exactly what we say before, and we use the general term of this table, and it's related to the derivative of in some formula, you see, it's mn, you have mn So this is the term of the tableau. It would be interesting to look more carefully. I have the book in my computer.
Oh, you
I have a copy, photo of the book, I think. Okay, let's go back to our subject, the Catalan garden. So there was an exercise to give a bijective proof for Catalan number, but we have already seen two bijective proofs for the Catalan number. This bijective proof using the cyclic lemma. We have seen this bijective proof using with complete binary tree and choosing. So this formula is equivalent to this one easily. But there was an exercise to show this formula. And if you want a bijection for this, if you don't move if you don't say that this is equal to this, okay, it's very easy. But if you don't move anything, then the bijection is going to be totally different than this one. So this was an exercise. So I give you the solution of the exercise. So I put it like this: n plus 1 times Catalan equal 2n choose n. And I give you the solution of the exercise. So Catalan is a binary tree. I take complete binary tree. And n plus 1 is the choice of one of the leaf of the complete binary tree. So if you look carefully what happens, you see you have the path going from the root of the binary tree to the leaf. And along this path there is some trees are attached to the path. Sometimes they are on the right. Sometimes they are on the left. I have to show that this kind of picture is exactly in bijection with 2n choose n, which is a number of paths going from 0 to 0. They can go up and down even below the x-axis. So these are called bilateral dict paths. It's words having the same number of x and x bar. You don't ask that the path is above the x-axis. So any word elements 2n with n times x and times x bar will be counted by 2n choose n. So this is bilateral dict path. This is pointed binary tree. And you get the bijection. So each tree pounding on the right give you a primitive dict path. Primitive means that it's not the power of another product of dict path, which means the path is always above the level 1 except at the first step, the last step. So you have a second. Now on the left we have other primitive dict paths, which are, I put them in red, them in blue. Blue to go the right, red to go the left, as usual in politics in France. And so the first, you have a sequence of blue primitive dict path, then a sequence of red primitive dict path, then a sequence of blue primitive dict path. So if you just reverse this, the red, putting them below, you put them all together, you get a path of length 2n, which is counted by 2n choose n, and so this gives the proof of the bijective proof of the formula. So you see it's totally different than the other formula with a cyclic lemma with 2n plus 1. Here I have 2n, but I have given you the solution of this. I give you another exercise. Prove this with dict path, not with trees, dict path. So this is a dict path of length 2n. n plus 1. 1 means keep the dict path. So you keep it. A dict path gives you a bilateral dict path. Or else, n times, you choose one of the northeast step. Choose one of the northeast step and do something to get a bilateral dict path, which is not a dict path. So try this. This is a little more, but maybe not so obvious. And this is another bijective proof using dict path, totally different also. Okay, now I claim in one of the chapters that I will prove the Lagrange inversion formula. I will prove it using the cyclic lemma. I will prove it only in the case there was a general function g of t equal t. So I remind you the Lagrange formula, the special case where there was only the function phi and not the function g. So I have a function phi of t a generating function, the power series, with a constant term is not 0. And I am looking for y, another power series, the unique solution of this equation. The unique solution of y equal t phi of y, and you see that y will start with t, so y of the constant term of y is 0, and there is a unique solution of this in a formal way. There is a unique solution of this, and the Lagrange inversion formula tell you that the coefficient, you can compute y, the coefficient of t power n in y is exactly 1 over n divided by multiplied by the coefficient of t n minus 1 in phi of t power n. So this is the Lagrange inversion formula in the case of g equal reduced to t. When there was a general g, it was g of y, and I have to multiply by the derivative of g here, but I will prove only in this case with the cyclic lemma and a bijective proof using path and word. So I have two lemmas to prove this inversion formula. I will use Lukasiewicz path or Lukasiewicz word. So I recall the definition of the previous, or the beginning of chapter 2. So path is a Lukasiewicz path, a sequence of vertex S0, S2, Sn. Each elementary step you can jump. Each elementary step is of this type. If you are at level y index I, then you can go at level -1, stay at same level, or jump any height you want. So it's an extension of Dick path and Dick language. This is an example of a Lukasiewicz path. So here I have jump of at level 2, then I go down, then I have some level, etc. So each Lukasiewicz path can be encoded by a sequence of letters, which I'll call Lukasiewicz language. So the Lukasiewicz language is the alphabet is x index -1, 0, etc. xp, and I have a morphism, a monoid morphism for the free monoid to the integer z. And Lukasiewicz language, it's exactly the set of words satisfying these two conditions. The delta of w is -1, delta of xi is I, which means the product of all, the sum of all these indices in the world will be -1. And for every left factor u of w, that is w equal uv, then the delta of u is positive or 0. So this means that if you write the language L, the words W, as a sequence of step, each step, when you have x in this I, mean you go from level to level plus I may be -1, 0, 1, 2, 3, etc. So this word is encoded, is visualized by this path. So this is the blue, the Lukasiewicz path, Lukasiewicz language. We are always above the x-axis. This is condition 1, no, condition 2. And at the end, you go to level -1. So the delta of the word is -1, and delta of every prefix of the word is positive or 0. So this is analog of the, before we have the language A equal a dick words multiplied by x bar. This is the analog where you can jump going up. Instead of x, you can go any level up. Now I am going to relate the Lukasiewicz language with my function y and phi. So an, you remember an was the function phi in the Lagrange inversion formula. So an was the coefficient of t power n in the function phi of t. So now I am going to relate an. So we have a monoid morphism from the free monoid to the set of polynomial with product of polynomial. h of the letter x n minus 1 is going to be an multiplied by t. Which means when you go down level minus 1, you put a0t. When you have a level, you put a1t. If you go up one level like x, you put a2, t2, etc.
So T counts the number of steps.
T counts the number of steps. And the difference of level you are going, it's exactly the index. So when you go down one level, when you go minus 1, it's going to be the constant term. And if you are at a level, you will get t, etc., t2, t3, t4. So first lemma, the unique solution I am looking for, Lagrange-Urgent formula, y of the equation y equal t phi of y, is exactly the sum over all words of the Lukashevich language multiplied by the morphism h of w. So you see, when you take a word of length n, you will get a monomial of t power n, and the coefficient in front of the will be the product of all the a index, the difference of level for each letters. So proof of this lemma. For p, I take any p, I divide the Lukashevich language in a partition. I partition all the words of the Lukashevich language in L index p, where L index p is a set of words such that it starts, I look the first letter of W, it's x index p multiplied by another word. P may be minus 1, 0, etc. P is bigger or equal to minus 1. This is the first letter of W. And I claim that any words of LP has a unique factorization, xp multiplied by v1, v2, vp plus 1, where each vi is a Lukashevich words. This unique factorization looks like the one we have seen before. If you take now a Lukashevich word, so you jump maybe at level minus 1, maybe 0, maybe here p equals 3, you jump immediately at the level 3, and then again you have a unique factorization. You look the first time you reach the level p minus 1, always above p, and then the first time you reach this level, now you go, and the first time you reach p minus 2, third time you reach p minus 3, etc., until you reach 0, and then there is one more step to go to minus 1. Because Lukashevich language, always you have the last letters is an x bar. All the part is above the positive axis, except the last letter go like this. And you see your factor v1, v2, v3, vp plus 1. Each of these words is the Lukashevich word. It's a green portion multiplied by the red letters. Now you understand better what I defined last time, Lukashevich word, where I put a minus 1 at the end, an x bar at the end. So in a word, this unique factorization. So I can write, if I apply the morphism h, the sum of all the words Lukashevich, which is going to give me the unique solution y I am looking for. It's a sum over all p. So the LP give a partition of Lukashevich into this subset looking at the first letter. And h of w is going to be, so the product, it's a morphism, h, so the product of all the individual words of the unique factorization multiply the h of the first letters, which is a p plus 1 t. There is a shift by 1 in the... And this is exactly h of w power n, because p plus 1 is going to be n. There is a shift by 1, so this is exactly sigma over n of a and t multiplied by this. The product, n times, n equal p plus 1, product n times of this, n equal p plus 1, so a p equal a n minus 1, there is a shift by 1 in the morphism h, and this is equal to this. You have to remember the morphism H is xn minus 1 equal a n t. So that when you go down, if you have x minus 1, this would be a 0 t. So I have proved my first lemma. To get the unique solution y of my functional equation, it's just to get the image by the morphism H of all the Lukashevich words, where I replace each letters x index p by a index p minus 1. And now the second lemma, I am going to apply the cyclic lemma. So the cyclic lemma for Lukashevich words, it's word exactly the same. I can apply the general cyclic lemma for Lukashevich word with a p for any p, the same lemma works. But here I need only p equal 1. So I need extension of the cyclic lemma for Lukashevich word, in the case p equal 1. And this was a paper by Rane in 1960. So every word, I just repeat, it's the same proof. What I have done for Dick path works exactly the same for Lukashevich path. All the factorization, the picture are the same. And so any words in W star, in the Lukashevich, in the letters x minus 1, x0, x1, x2 in the x star, as any word, so that the delta of W is minus 1. At the end, it finishes with minus 1. Any word like this has a unique factorization. Something wrong? It's
Then P is minus 1.
p equal 1.
Minus c.
Minus p equal minus 1, yes. No, p, wait. Sorry, p equal minus, no, it was minus p, yes, in the, p was the positive numbers. P equal 1 is the same, right? So delta of W is minus 1, p equal 1. The path finish at level minus 1, so at level minus p. So I apply the cyclic lemma, more general for the Lukashevich words, but in the case p equal 1. All the proof is the same for Lukashevich. So there is, if you take a word in the such that delta of W equal minus 1, there's a unique conjugate. There exists a unique conjugate of the word in the Lukashevich language. So if you take any word product of letter, I just repeat the same proof. In the case of Lukashevich, take the smallest integer and say the proof is this. Yes?
Cyclic lemma, we said that there are
Cyclic.
three conjugates in A star, right?
Yes, yes.
So here you're not using L star, it's only
I am only A because when I say the first cyclic lemma for Dick words, in the case P, general P, there was P different conjugate in A star. A star is a product of words of A, but as soon as delta of the word is minus P and it is a product of word of A, then it's in fact in A power P. It's a product of P words of A. Now to say that the conjugate is going to be in A star, in fact it's in A. The Lukashevich language itself, it's a P equal 1, so the product of words in A star will be only one word in that case, and A in that case is L. So see again the conjugate, you take any words in the alphabet x minus 1, x0, x1, x2, etc. And you cut the first time you reach the minimum, and you do the conjugate like this. So it's exactly the same as before, but only p equal 1. In that case, I don't have to make p time p conjugate, but in the general case of Lukashevich. So it's work exactly the same. So, and you can check that the only way to get a conjugate in Lukashevich language, the only way is to do this. There is only one position, and you do this, and you get a word in the Lukashevich language. You see, all this portion here, it's going to be added here. And when the last point here is going to be at this level. See, the last point here is this level. And then at the end, you go below minus 1, the blue level. Which is a visualization of a Lukashevich word. If you start at this level, all the green part will be at above the blue level, and at the end, before the red edges, you reach the blue level. So this is a Lukasiewicz word finished by an X bar. And this is the only possible conjugate. So now you apply and make a change of notation. The morphism was associating to each letter a and t, so I just consider now the coefficient an. So I put h0, means I don't put the variable t. So the h of w is going to be this constant coefficient with t power the. And so I can write by lemma 1 the coefficient of t power n in y. Y was the sum of all the h of w, so now by the change of notation, the coefficient of t power n in y is exactly the sum over all possible Lukasiewicz words of h0 of w. So h0 is going to be the product of all the coefficients of the constant associated to each letter of w. This is lemma 1. Now by cyclic lemma, if you take all possible words finishing at level -1, there is only one conjugate which will be in L. So this is a division by n. The length is n. So n times there is n possible conjugate. Only one of them will be in L. And now we have to say that so this is a coefficient of t power n in y equal 1 over n multiply. I have to say that this is a coefficient of t power n minus 1 in phi of t power n. So the last step of the proof is to see that this is exactly equal to this. So why? If you take words of length n finishing at level -1, any word, then this is the coefficient. This can be written as the coefficient in phi of t power n, the coefficient of t power n minus 1. To give the proof, I give you an example. It's because I take, for example, n equal 9. I have a Lukasiewicz word, any word of length 9, and each step going up or at a level which contribute to t power the difference of level. This is t, this is t3, t4, etc. And you can see that the t will contribute to t power 8, 3 plus 1 plus 4. You have t power 8 and the length is 9. So there is a difference of 1 between the length n, which is going to be the contribution of phi of t power n, and the coefficient. In fact, the t will be exactly t power n minus 1. The t coming from here will be 1 less than the length. We have to think a little about this, but think of this example where the length is n and the contribution, the number of times, the power of t which is going to appear is t power n minus 1. Which say I take the coefficient of t power n minus 1 in phi of t power n. Phi of t power n is, when I apply the first lemma, I apply h for all the letter, h0 for all the letter, the n letter of w. So this is the idea, combining this unique factorization of Lukasiewicz word, give you the unique solution y of y equal t times phi of y, combining with the cyclic lemma, give you this Lagrange inversion formula, coefficient of t power in y equal this. So it is a nice application of the cyclic lemma and Lukasiewicz. So today we have two principles. We have the cyclic principle, and we have also the reflection principle. It's a day of principle. Like the inclusion-exclusion principle. The whole chemistry is pigeonhole principle. There was many principles of methodology, so this is kind of a reflection principle. I will apply this twice. So proposition, I take any points A equal on the horizontal line, coordinate A is 0. I take a point A, I take a point B, which here you see at the axis is A plus M. M is the distance between these two projections, and this distance is B. So the coordinate of B is A plus M, and A plus M minus B. So this is B. So any 2 points A and B below the diagonal in purple, and I am interested to enumerate the set of paths. How many paths below the diagonal? Maybe they can touch the diagonal. This path is not in this set. How many paths? The set of paths starting in A, finishing in B, possibly touching the diagonal, but always below the diagonal, and with elementary step north and east. So the number of such paths is this difference of 2 binomial coefficients. So I am counting more general than dig paths. Dig paths are below diagonal. I am counting paths starting at any point below, total number of paths which go from A to B, which are below diagonal. It's the difference of 2 binomial coefficients. They are in the same row of the Pingala triangle. But totally, so you pick up any binomial coefficient in the Pingala triangle, the difference of the 2 coefficients on the same row will give you the number of paths which are below, which is a well-known fact since 3,000 years in India.
At one point it goes above there.
Oh no, this is this path. I have no time this morning to change, to delete this, and this path is not. So it should be below the purple diagonal. It can touch, but not cross. This one is bad. It's crossing the diagonal. So I'm going to prove this by using this reflection principle. So I put delta in red, the line of equation y equal x plus 1. I put the point A prime, which is the symmetric of A, according to the red line, delta. And then so what is the total number of paths going from A to B? Is this binomial coefficient? Total number of paths without consideration if it's below or not the diagonal. It's a set of paths starting in A, finishing in B with only north and south step. So such number is this is the total number of steps divided by M. M is the number of east step. There is M east step and there is M plus A minus B north step. So this is the total number of paths. And number of paths going from A prime to B is this binomial coefficient. It's again total number of steps divided by the number of north or east step. So I have these 2 binomial coefficients. And I claim that the number of paths below diagonal is the difference.
What is A prime?
A prime is the symmetric of A according to the line delta. So A prime has coordinate -1 and A plus 1.
Image of A, right? Not image, yeah. Image.
Is the symmetric of the point A according to the red line which I call delta. The line just above the diagonal. So I have these 2 sets of paths which are trivially enumerated by some binomial coefficient. Now you have to enumerate the paths below the diagonal. So I claim that the path having a non-empty intersection with delta. So you have to count this is total number of paths minus the paths which are below. So the paths which intersect delta are in bijection with the path going from A prime to B. Why there is this bijection? Take a path like this one, having a non-empty intersection, which I call I. So you take I, no, I is the first time the path in green touch the red line delta. Take the first time you do this, and then you define the path omega prime is obtained by reflecting the portion of the path omega between the A and I. You reflect it according to the red line, and to get a path in blue like this. So my green path, going from A to B, is in bisection to this path starting from A prime, portion in blue, and then I continue the green path omega. So this is a bisection I was looking for. And so the path here, which below the diagonal, means they don't touch the path below the diagonal, weakly below, means they don't touch the red line, and means there are the difference between these two paths. So this is easy methodology, easy principle, reflection principle. So some people say that Désiré André had solved the problem. It's usually called André reflection principle, but I read carefully. It seems that the proof is not using reflection principle. It's something slightly different, but it's called André reflection principle. So I get the proof from my proposition that the number of such paths below diagonal is the difference of two binomial coefficients. So if I take the special case A equal B equals 0, then my path going from A to B are in bisection with Dicke path. So I have this formula. The difference of the two binomial coefficients is going to be this. This is another formula for Catalan number with another bijective proof for another formula. So each formula fit very well with a certain. If it's too complicated, means you are not in the good object of the Catalan garden. Each formula, you should find the best object to prove the formula, which is the Catalan number Cm. So the Catalan appears also as a difference of the two biggest coefficients in the Pingala triangle. Another corollary now, I have a double distribution of Dicke words according to the longest sequence of x at the beginning and longest sequence of x bar at the end. Here is the Dicke words written as a ballot sequence. So you see the longest sequence of x at the beginning, this is xxxx, followed by, this would be an x bar. Here you have j, and followed by this. So this is the double distribution of Dicke path with this sequence. So you have just a slight change of notation. A and B are related to I and j like this, m equal n minus I. And so you have this formula, total number of Dicke paths, of Dicke words, with this double distribution I and j is equal to this difference of these two binomial coefficients. So you have,
Like that Catalan triangle is
yes,
J is 0.
now for j equal 1, no, j is always 1, at least 1. Yeah, there is only, so you get this, which would be equal to this, check. Please check that this equals this. So this is another proof of the Banach number, but this is, you say, there is a ratio which gives you the cyclic, the ratio means there is something cyclic, and the difference, there is something reflection. This is a symbol of the two methodology of today. Reflection principle, where you subtract something, the bad guy are subtracted from the good, and this is cyclic, when you have directly the ratio of Allez, second time, the reflection principle again. Now we go to the third distribution. The main distribution in Catalan garden is a beta distribution. We have seen alpha distribution, but the beta distribution is you are counting Dicke paths or Dicke words by the number of peak. Peak is a factor x followed by x bar. So what is the number of Dicke words of length 2n having k peak? This is a nice formula, which is called the beta distribution. So I am going to give you the formula by changing my Dicke path into staircase polygon. So you remember staircase polygon, the number of columns was exactly the number of peak of the Dicke path. So we have to count this by number of columns. So I have to count this. So I put my point A1, A2, like this. I put B1, B2, like this. So see, I define my 4 points, A1, A2, B1, B2, and B, the corner of the... So it's a staircase polygon, or it's contained by Catalan number Cn, so the length is n plus 1. K, the number of columns, and total length between A2 and B is n plus 1. So I call Aij, it's a 2 by 2 matrix. Number of paths, they guess the solution. Number of paths going from Ai to Bj for I and j between 1 and 2. So this matrix, total number of paths going from A1 to B1, A1 to B2, B2 to A1, and B2 to B2. So I have 4 binomial coefficients. Right, this binomial coefficient, now you go back to the number of paths A1, B1, number of paths going from this to this, from A1 to B2, and from A2 to B1. So you look carefully, the length of the path, the number of each step, and you get this 2 by 2 matrix. In fact, this is a general 2 by 2 minor of the Pincalad triangle again. The 2 by 2 minor of consecutive row, consecutive column. So if you take the sum of all these 2 by 2 minor, this should give the Catalan number. It's a consequence of what I am going to say. The proposition is that the number of pair of paths, omega eta, such as that the paths go from 0, 0 to B, with only north and south step, they don't intersect except at the extreme point. So the total number of polygon, of staircase polygon with k column is equal to the determinant of the matrix A, the 2 by 2 determinant. So this is the product of this by this minus this, and I claim that this determinant is equal to this. There is a nice formula for the 2 by 2 determinant, which is the product of 2 binomial minus the product of 2 binomial. There is a formula, and this is called usually the Narayana numbers. This is a beta distribution. This is going to be the number of disk paths of length 2n having k peak. This is this number, Narayana number, is a beta distribution. If you put a variable x power k, this will give you the Narayana polynomial. So I give you a proof of the proposition. So proof, the determinant is the product of these two. It is the number of pair, a path here multiplied by a path here, and minus this one. This coefficient is the number of pair of paths like this. So I have to find a bijection between paths, the product like this, with paths like this, which intersect. So if I have a bijection in this, the paths from this term which are intersecting is going to kill the pair of paths going from this. So what will remain is only the path in this going from A1 to B1, A2 to B2, which does not intersect. That is the number of staircase polygon. So the bijection is again very simple. You take the two paths omega eta, you suppose they intersect. The bijection is between paths which intersect. Suppose they intersect somewhere. So you take the first point where they intersect, and then you interchange. So you can interchange the beginning or the last.
Same local proof of LGV lemma, right?
Yes. This is chapter 5. Chapter 5, LGV lemma will be in the case of many paths, k by k determinant, a big determinant. And so this is to prepare you for the general lemma about non-intersecting paths. And this will be chapter 5, which will give us at least three lectures on chapter 5, tiling, determinant, and non-crossing paths. So it's a special case of two paths. So you see, the first time I cross, and then to change. Before I was, for the first time reflection, I was exchanging the beginning. Now I change to play with the reflection lemma. I just exchange the last two parts. So omega, you see, omega is this path in red, and then I interchange the blue in the red part, so omega becomes this one. And so interchanging, you have a bijection between this and this. And so this is give you a proof of the theorem. So I have three distributions. This is Crevera's notation, who was a big expert in Catalan and 50 years ago. He called alpha, beta, gamma, the three distribution. So we have the alpha distribution, which is the Banach number. So you can repeat, by using the bijection of the beginning of chapter 2, you can repeat the alpha distribution, which was defined like this. You can put it in all the bijection, and it's going to give this. This will be also interpreted as a number of time in the disk path you touch this axis. So this parameter is going to be exchanged with this one, the same distribution. Why? It's because if you take a bijection between disk path and binary tree, the length of total length of the first sequence of x will become the length of the left branch of the binary tree. Then you exchange, make a symmetric mirror image of the binary tree. So this is going to be the right branches. Go back to the disk path and you get this. So you go from this to this by going the binary tree, symmetry of the binary tree, and coming back to the disk path, and you get this parameter becomes this one. So it's the number of, in any disk path, the number of terms in the primitive factorization in primitive disk path is the same as the alpha distribution. It's the length of the left branch, and of course the length of the right branch. Well, you have to check this, that if you take a binary tree, the length of the right branch will become the number of times the path touch the x-axis. Now for planar tree, the parameter will be now the number of a subtree of the planar tree. The number of child of the root of the planar tree. Planar tree is n+1 vertices are contained by Catalan number, and this is the high, because it's going to be the number of primitive factor in the word. This corresponds to each primitive factor in the disk path. Staircase polygon, it's the length of the first column. And in non-crossing partition, the number of blocks. Go back to the bijection between disk path and non-crossing partition. Each block was a consecutive sequence of edges going down. So this is exactly in bijection with the peak of the disk path. So this is the non-crossing partition. So very easily with the bijection, you can transport your, once you approve the formula in one of the objects, then you can transport immediately to the other. The second distribution, the beta distribution, the number of peaks in the disk path. So this was the definition, and we have seen that we have given the formula by using the bijection with staircase polygon and using the 2x2 determinant. Of course, I did not prove that the 2x2 determinant was equal to this. You have to check easy calculus. So it disk path by number of peaks. It's planar trees by number of leaves. The peak of the disk path in the classical bijection is going to be the leaves of the planar tree. Now if I take binary tree, in a complete binary tree, where you have external edges, they can be to the left or to the right. So if you count the number of of edges going to the left, this will be the beta distribution. Or it can be also in a binary tree, in a general binary tree. You count the number of left edges plus 1. Inside the binary tree, complete is only external edges. General binary tree is inside the tree. And staircase polygon, the number of columns. We have seen the basic, the first example to get the formula. Now we have two bijections between staircase polygon and a bijection with two column Hodgkin path. So the k, the number of columns, becomes the number of steps of this type or of this type. If you can't just check in the two column Hodgkin path, it's easy in the bijection. Number of columns is going to be the number of steps like this or step the red level. Now from this I go to disk path, and now I have something very interesting, is that this number of going up or red level becomes exactly this red step. It becomes the number of southeast step going from an odd level to an even level. Going from 1 to 0 or 3 to 2. So you say you take you take each level, you go 2 by 2. In the first strip, you put some red edges going down. In the second strip, you do nothing. In this strip, you put again red. So you go 2 by 2, and each time you go down from an odd level to an even level, you specify your red edges. No, total number of such South steps give you the beta distribution. So you have to go from this to this, and then from this to this. So the peak, and if you go back to the dig path, the peak of the dig path becomes this kind of step. And I claim that this is very interesting because you will see in chapter 5, using the LGV-Leba non-crossing path, we will have a determinant of Schroeder numbers, and this determinant can be computed without any calculus by using this bijection. By using this interpretation, going from the peak to this step. You will see at the end of the class. And I will get the number of tiling of the Aztec diamond bijective move without any calculus, applying twice the LGV lemma and this bijection. And finally, the third distribution, the gamma distribution, is a ratio of Fibonacci. So the gamma distribution is the height, maximum height of the dig path. We have seen there is no explicit formula, it's a rational fraction. The genetic function for dig path with bounded height. The special case was a logarithmic height, which is a Strahler distribution. It's a special case of this distribution. We have done a lot of remark on the Strahler number of a binary tree. So it is just the height of a dig path. So the height of a dig path bounded by this height are given by this. If you want explicit height, you have to take the difference between k and k, the same rational fraction for k minus 1. So the height of the dig path is going to be the height of the planar tree, and inside the binary tree is going to be only the left height. See, the left height of a vertex in a binary tree is you take the unique path going from the root to the vertex. The left height is the number of left edges going in this path, and the maximum of this number of left edges for all the vertices S is called the left height of the binary tree. So this is also given by the gamma distribution. I think there was a question last time for the total height of the tree. So this is much more complicated. It's not at all, it's a parameter which was done by Flageolet and Odlyzko. This is not so nice at the maximum left height of a binary tree. So it's, you have no time to do so I cannot finish chapter 2. Sorry, Suresh. I will, maybe I have 5 minutes to give a compliment, something compliment. The complement will be the solution of an exercise. So I will get the solution of the exercise about pyramid, semi-pyramid. You remember I asked to prove that the number of semi-pyramid with n dimers was the Catalan numbers. So here is a semi-pyramid. You take, maybe if it's empty, if the semi-pyramid is, if there is no dimers, it's 1. If there is dimers here, so maybe there is somebody below. If there is nobody, this will be empty. But if there is somebody below the maximum dimers, I take this and I push. Suppose you push, the first dimer which is below, you push it. And what remains is another semi-pyramid, if you want to put really as the hips. So I have decomposed a semi-pyramid into a product, a semi-pyramid, multiplied by this and a shifted semi-pyramid. So it gives me this equation. Y equal 1 empty semi-pyramid plus T, this blue dimers, multiplied by Y, multiplied by Y. And so this gives me Catalan numbers. No, but what is about a bijection? So I have a unique decomposition, Y and Y, and dig path. I can also have a unique decomposition. So if you recursively apply the same idea that if you know bijection, small bijection for small semi-pyramid, you can extend it to bigger pyramids. And here is the result. I give you the bijection. one possible bijection. So I have a dick path. I'm going to rotate the dick path 90 degrees. The dick path is going to be like this. And it's going to give me semi-pyramid of diamonds. So look, it's a video which gives you a bijection. Et voilà. The bijection between, which is automatically constructed from the recursive decomposition. Okay, thank you very much. So next time I will finish chapter 2.